Okay, let's do it. Oh, oh we're going. Okay. Um, okay, so let me, I guess you guys are going on the project. Let's do this Friday. Uh, oh, next Friday. Oh. Next Wednesday, next Wednesday, next Wednesday. Got some extra time now, so you can do even better, right? So it's good. Okay, so let me give you some suggestions, but I won't give you secret suggestions. I'll give you in joke. Okay, so some of you ask about what's a good number to look at. Okay, I mean, well, what should you be striving for? Okay, let me give you a way to sort of get an estimate and a little bit of a topological approach. Okay, so here, let's say you have several stages that look like this. This is kind of, it could be diff pairs, but this is, in essence, you have something that looks like this. You're trying to get gain, okay? And let's look at the bandwidth of this stage, okay? Let's say these transistors are all about the same size, okay? Now, so what's the bandwidth going to be of this first stage? Well, it's going to be, or of the output here, sort of the output node. Mega 3 dB is going to be 1 over R out of this stage, okay, times the capacitance of the next stage. Now, the capacitance of the next stage is going to be composed of CGS, and for this circuit, it's going to be a C Miller, right, potentially, because you have a lot of gain in this next stage. Of course, we can get rid of the C Miller by cascoding this, okay? So I'm trying to get sort of fundamental limits in some sense, okay? So let's say I cascode this thing, right? Put a little cascode device here. So I end up with only seeing really CGS and, there's CGB and some of those other things, but they're pretty small compared to CGS. So CGS pretty much dominates, okay? So let's say 3D, it's roughly, this is very, very, very roughly, R out times CGS, okay? What's the gain of this circuit? Gain of this circuit is A0, the low frequency gain, is minus GM times R out, okay? So the gain bandwidth product, I told you about this the other day, right? You multiply these two things together for this kind of stage. Now, of course, you notice I put in that cascoding to make sure I didn't get the extra Miller capacitance. Okay, so I've fixed the stage up so it's a pretty good one. The gain bandwidth is going to be equal to this times this, and you can see what happens. I get, take magnitudes here. We get GM R out over R out CGS. So I end up with sort of GM over CGS is the gain bandwidth product. Okay? So if I change the gain, I'll reduce the bandwidth. Or if I increase the gain, I'll increase the bandwidth. Similarly, think about this. If I reduce the gain, I increase the bandwidth. Okay? So now how can we use that? So let's take a couple of different circuits. Let's take circuit A, where I have gain 1,000, okay, and it has sort of an R out, and it drives some capacitance, okay. And if we say the gain bandwidth product is roughly GM over CGS, okay, this is driving some other capacitor here, the output stage, let's say. So let's call GBW is our. This is almost for the it's almost related to the process, right? Because GM, you think about what it's. If you go through the numbers on this, you're down to sort of the parameters of the technology you have. 0.13 micron will give you one value for GM over CGS. I should go through that for you. I can do it roughly. GM goes as it's fundamental. It's a function of the process, and very strongly a function of the line length, the 0.13 micron. number we have for this process we have now. The next generation will be 90 nanometer, 0.09. That increases this number a lot. Okay, so that's a very strong function of the line width, the minimum channel length you have in your device. So that's kind of fun. So it's sort of fundamental to the process you have available to you. So you have 1.13 micron as your process you're working with. So you're kind of stuck with this gain bandwidth number. Okay, now, so let's call that gain bandwidth for whatever process you have. We'll call it GBW0. Okay. Now, we have a choice here. Let's say we take a gain of 1,000. So what's the bandwidth going to be? It's going to be that gain bandwidth product for this process divided by 1,000. And that will give what your bandwidth will be. Okay? Now, let's do another circuit. Let's do another approach. Let's take 3 stages of gain. Yes? This was my idea. This wasn't your idea. This was his. Huh? I won't give other people's. I would come in and give their really good ideas in lecture, and so I'm not going to do that. But this was my idea. This is an important one, right? My ideas I can share, right? I won't share your ideas. So times 10. So let's do 3 stages of times 10. Okay. And what happens is that what you can do is the bandwidth now, okay, is going to be equal to the gain bandwidth product number we had divided by 10. Okay? So you can see now what happens is that the bandwidth is basically going to be 100 times higher than the bandwidth here. Now we have 3 of those in a row. And that will, of course, degrade the bandwidth a bit by putting a whole bunch of stages of about approximately the same bandwidth. It won't be quite the same as the bandwidth of one stage if you have, but in actual fact, it'll still be a lot more than this. So, fundamental thing to high frequency design is more stages of lower gain is really what makes it. That's how you get faster circuits to work, right? And it all comes from this gain bandwidth product thing. Different topologies will have different gain bandwidth products, okay? But it's hard. It's really hard to beat this number right here. And so if you want to get an estimate of what's good or bad for your circuit, calculate GM over CGS of one of your transistors, figure out what gains you're asking for, and you can sort of see if you're getting a reasonable bandwidth, right? You can see if you didn't cascode this, you get well below this number, right? Because the Miller capacitance would come in. And you would see, well, you're well below what you could do if you sort of fix the circuit up a little bit by cascoding it. Then the other good idea we had in office hours. All right. Any questions about the project? So let me just say some words about the specs. Okay, so what I would say, you should basically start with the circuit you had before, because we didn't change any of the output swing specs. All that stuff has stayed the same. We did that for a reason, to make it easier for you this time. What we're asking for you to do is the low frequency pole. You'll have a whole bunch of other poles, but we're worried about the lowest frequency pole. And you get to that as the highest frequency as possible. That's the bandwidth of the circuit. The bandwidth of the circuit is set by the lowest frequency pole. That's what we mean by bandwidth, okay? We're asking you that common mode gain has to meet that spec all over that bandwidth. So where the lowest frequency pole, this is the differential mode gain as a function of frequency, right? But you got to check to make sure your common mode gain doesn't degrade, because I told you about the problem of, output, the capacitance on the tail current source can degrade the output resistance of the tail current source, which can degrade your common mode gain, right? I discussed that last lecture. Yeah? Less than 0.1, yeah, right. Yeah, ACM should be less than 0.1, not greater than 0.1. Yeah, that'd be easy spec, right? So you try to make this as high as possible, make sure ACM stays the same, and meet all the other specs you had from the last project. Yes?
Did you say you were going to talk about how people got hundreds on the project?
Did that get... Yeah, I was going to put them online. That happened? Did the project get Okay, I will talk about the I'm sorry, I asked them. I'll do it. Okay, I'll check on that. Okay, the report. Okay, let's talk about that. Okay, so the reports. This time, you're not going to have to do all the hand calculations of the DC stuff that you did last time, right? So you don't need to do that. I'd say roughly, you could easily do 2 pages, would be just fine, plus a schematic, okay? Okay. And in the 2 pages, the things I'm interested in are, one is a hand calculation of the lowest minimum. Here's the minimum. You can do more in these 2 pages, but the minimum is the hand calculation of the lowest frequency pole. And I guess also a little bit, if the common mode gain degrades, well, it can't, right? You have to keep it up there. So hand calculation lowest frequency pole of omega 3 dB, okay? Some discussion of your design, your approach, to maximizing the FOM, right? The 3D bandwidth. And then any other things you learned about during this design process, I guess. I mean, so things that showed that you really, other approaches you took, or things that you've discovered, well, what worked really well here that didn't work. It showed me you learned something from this project. Yeah.
So can you say what exactly?
Here's your mic.
Can you say what exactly gave people who got hundreds to?
They got a really good figure of merit. That didn't make a big difference, right? Because I kind of compressed the quantity of that. They did a very easy to read set of hand calculations that I could understand what they were calculating, and went through very straightforwardly. They did a good analysis of why their circuit worked. Maybe they compared to other approaches they had taken and why this one was the best one. What else? Let's see. A lot had to do with, it was easy for me to go through that and figure out what was going on. That counted a lot. So ones that were really long and had lots of stuff in them, I couldn't figure out what was going on, I didn't reward. I didn't penalize, but I didn't give extra credit for it. Does that help? And they gave me a certain amount of money, which you didn't do. That was the problem. That's the unknown value, right? I won't count. It really was hard for me to grade those, like that English, sort of essay grading problem, right? Which is not fun for me to do. So this time I only want 2 pages, and I would guess unless you don't do the minimal amount of work and do something that explains what approach you took, do the hand calculation, you will get the credit for it, right? It's going to be hard to excel because I don't have not much stuff to do here, right? So I would guess there won't be a big differentiator in that part. Tell me what you learned. If you can explain to me something that you learned, what you learned in that project, I guess that's kind of what when you did the trade-offs and just tried different sorts of topologies. What did you find? What did you find out? I'm just trying to figure out that you got something out of it. That's, I guess, my goal. Right. Does that help?
State data report, what we learned.
Yeah. Through the figure of merit kind of stuff, right? You know what? In B. Yeah. Okay. Any other questions? Feedback. Okay. Last time we got to so what are we doing? What we are doing is analyzing a circuit like this. Okay, this is and I'm going to start giving them names to it. Series shunt is what this is called. Now, what this is all about, why is it called that? Okay. So here's our basic feedback circuit, okay? As I said, this could be currents in and voltages in, or currents out and voltages out. For the case of voltage in and voltage out, we call it series shunt. Now, why do we call it series shunt? Now, let me show you a way to redraw this. This is the feedback network right here, this part right here, right? So a feed forward amplifier here, feedback amplifier here, includes this resistor as part of the feedback network. Notice we're sensing a voltage and we're feeding back a voltage, and the voltage is differenced with the input. Okay, so here's the error voltage being, this should be error here, is being difference. So V error is equal to V in minus V feedback, and V feedback is created right at this node here. Okay, so let's redraw this like this. So here's V in, here's V in. Now I'm drawing it to ground. So here's V in to ground. Okay, didn't show a ground here. I'll put a ground in. Okay, here's the basic amplifier. You read this? See this? So here's the basic amplifier, here's the basic amplifier, here's its input resistance, okay? Here's the feedback network output, so here's the output of the feedback network. Here's F times V out, okay? So this side's grounded, so here's it's grounded, so here's the feedback network. And if we look on the other side, so we're sensing the output of the amplifier. So here's the output of the amplifier. Here's R0, the output resistance of the amplifier. That's the input to the feedback network. Here's the input to the feedback network. So this circuit here is just a realization of this, but showing it with two ports. Okay. So let's work with, this circuit down here, just to redraw this for you, is basically this. Here's R2 and here's R1. So this is that network here, okay? It's a passive network. Okay, why do we call this series shunt? Series, the first name here, okay, is the type of feedback. This is series feedback. You can see here's the input, and in series with the input is the feedback voltage, and we create V error, right? So there's a series combination of the input and the feedback, so we call this series feedback. Okay, the second name here is the type of sensing. We're sensing. Shunt means parallel. Shunt equals parallel. Shunt, the output voltage here is sensing the output, input to the feedback network is sensing the output of the basic amplifier in parallel. See, it's in parallel? Okay. So this is in series, and this is in shunt, parallel. So we call it series shunt feedback. Series shunt feedback is voltage feedback with voltage sensing. We're sensing a voltage, and we are feeding back a voltage. So this is a voltage feedback type. Okay? All right. Look here. We sense a voltage. We're sensing this voltage. It goes into our feedback network, and we're feeding back a voltage, which is in series with our input. Okay? Series shunt feedback. Okay, so now let's go through the rest of the calculations on this thing. And let's work with this network right here. And you can sort of do V out equals AV times V error. This is the definition of the basic amplifier. This is the definition of the feedback amplifier. I mean, V feedback is equal to the input voltage, which is the output of the, V in of the feedback network equals V out of the circuit. Okay. V in this series feedback configuration, look at that. It's V in equals V error plus V feedback, right? Because it's a series combination here. So V in equals V error plus V feedback. But V error we have we can solve for V air from this equation. We get V out over the voltage gain of the open loop basic amplifier. V feedback is equal to FV, the feedback factor, times the output voltage. I can solve for V out over V in, and I get this formula that I solved last time. 1 over the feedback factor times T over 1 plus T. And remember, T was equal to the loop gain. T was equal to A of the basic amplifier. Now notice the voltage. We're keeping track now of what kind of amplification this is. It's voltage amplification. It's voltage in, voltage out. So we'll have to keep track of that because we're going to start mixing currents and voltages together in a second. And times the feedback factor, which is also a voltage in, voltage out ratio. Okay? So this is the loop gain. The loop gain, these are both have units. They're unitless, right? Loop gain's always unitless. We will find sometimes we'll have these will have units in a second. Okay. All right. Okay, so this is the closed loop gain. 1 over the feedback factor times T over 1 plus T. If we take this formula here, we can solve for V in times V air, right? Just divide this out. Just taking this formula here, we can turn it into this. We can, how do we get to here? Vn just comes, this just comes from this formula up here, right? We can rewrite this, all right? What I'm going to do now is calculate the effective input resistance to this circuit, okay? What's the input resistance looking into the basic, looking into this feedback network? In other words, looking into here, what is Rn? So this is the closed loop input resistance, okay? Rn, little rn, is the open loop input resistance. I'm looking now for the closed loop input resistance. This is the input resistance of the circuit with feedback, okay? All right, little teeny bit of math. I guess I did output resistance first. It's Vn over In, right? So that's just, this is Vn. We need to find out what In. So, or this could be V test over I test. Vn equals 1 plus T times V air, as I just showed you in the previous diagram. In equals V air over Rn. In other words, the current here is just V air divided by Rn. So we can find I in is equal to just V air over Rn. So I'm just, that's just little, that's just this. I can substitute this V air for this V air here. I end up with this expression right here. So this is pretty simple math, and you can do it yourself. Rn equals 1 plus the loop gain times the input resistance of the basic amplifier. Okay? Rn was the basic amplifier. So in other words, what happens is when you put this thing into feedback, the input resistance goes up by the loop gain. And remember, the loop gain is very large, or can be very large. If F is 0.1 and AV is 10 to the 6th, that means, oops, I'm sorry. If F is 0.1 and AV is 10 to the 6th, then that means T is equal to 10 to the 5th. And that means that our input resistance is going to be equal to 10 to the 5th times the input resistance of the basic amplifier. So we get this huge multiplication factor. Pretty interesting, okay? What about output resistance? Output resistance is on my other page here. V test, we can force an output into the, do our little test voltage thing, put a V test here. Right? We can calculate I test. All right? That's what I did here. You can find out the current I test is going to be V test minus AV times V air, because this is the voltage in the basic amplifier, divided by R0, so that's I test. We can use our little formula for V air, go through all that, and we end up with this answer right here. R out is equal to R0 divided by 1 plus T. The output resistance of the basic amplifier divided by 1 plus the loop gain. So there's the formulas. So we've got three formulas now. We have, so let me just summarize the three formulas. For series shunt, okay, the loop gain, this is voltage in, because the type of feedback is the type of input you have. So it's sort of voltage in, voltage out, okay? Type of sensing. You sense the output, so it's a sensing of voltage in shunt. So it's voltage in, voltage out. So it's the a voltage amplifier, and this is equal to 1 over F times T over 1 plus T. And if T is much, much greater than 1, you can see this thing goes to 1 over F, 1 over the feedback factor. Rn, the input resistance of this thing, is going to be Rn of the basic amplifier times 1 plus T. R out is equal to R out of the basic amplifier, it's RO or R out, RO, divided by 1 plus T. So you think about what's an ideal amplifier, voltage amplifier look like? Here's V out and here's V in. An ideal amplifier, an ideal voltage amplifier has a real infinite, very large Rn, right? That's what you'd like to have because you want to drive from a voltage source, right? You'd like to have an open circuit that you drive. So a voltage amplifier, ideally, it's like a source follower, right? Source follower has a really high, it's infinite, basically, right? Now, for MOS, a lot of our amplifiers have very high input resistance, right? Because we go into a gate. But for example, a common gate amplifier doesn't have a high input resistance, so it's not a good voltage amplifier, right? What do we like ideally for a voltage amplifier output? We like to have really low output resistance. We like it to be a perfect voltage source. So look what this feedback does. It makes the output resistance small. It takes the basic amplifier, and we put some feedback around it, right? So when I do this, put feedback around it, and this should go back to here, right? This is R out. This feedback makes the output resistance smaller, right? It seems to be smaller. It gets smaller. Input resistance gets larger. It makes it a more perfect voltage amplifier. So that's the way to think about these things. You can remember all these formulas, but if it's voltage in, voltage output, what negative feedback does is makes it all better, right? It makes the output resistance smaller and makes the input resistance larger. And the gain's like this. Yes. Mike, where's your mic?
But then the gain is crap, right?
And the gain's crap. That's exactly right. Okay, so I mean, what have we traded off here, right? No free lunch. Okay. All right. But here's the important thing here. So let's look at this formula right here. Well, AV equals 1 over F times T of 1 plus T. So this is AV, this is the basic amplifier gain, right, divided by 1 plus T. So what happened is the open loop, we traded off the open loop gain of the amplifier. We reduced it by 1 plus T, increased the input resistance by 1 plus T, and decreased the output resistance by 1 plus T. So 1 plus T is the really critical thing that's going on here. But what we did was trade gain for input and output resistance, and even more importantly, though, it allowed us to get now a very accurate value of gain. Think about it. If I ask you for a gain of 10, and think about all the variables, how difficult it would be for you to give me a precise value of 10 if you had it as a function of the GM and R zeros and all those kinds of things. It'd be really tough to do. But look what I can do here. F is equal to, what do we say, R1 over R1 plus R2. The gain of this thing, if T is large, all you have to do is get T large, becomes 1 over F. So it becomes 1 over F is equal to 1 plus R2 over R1. So I just have to ratio two resistors by a factor of 9, make these two resistors ratio by a factor of 9, and I get a very precise value of gain. Right? R1, R2, I guess. All right? So, precise value of gain, great input resistance, and great output resistance. So this is why you like to use op amps. Okay? All we have to do as designers is make the gain big. And we can get ideal characteristics otherwise. So that's why feedback is so nice. Any question about that? That's the basic idea here. Yeah. All right. Now we're going to do some other. Now there's 4 possibilities here. That was voltage in, voltage out. Let's do another one. Let's do a one that's current in, voltage out. Oh. Let me show you what a circuit would look like. In. Oh, jeez. Ah. Let's see here. We'll do this. Okay. Here's our basic amplifier right here. Okay. And so here's the Rn of the basic amplifier. Okay. Here's our R out. Here's our gain, A sub R times I air. And I air is the current going into this amplifier. And here's the output. So I have input resistance. Here's my output resistance. Now notice I'm creating an output voltage from an input current. So in other words, we have here V out over I air, okay, which is the current going right into this. I'm going to put something else here in a second, so let me not, is equal to AR, right? All right, this is open circuit, okay? So we have, this has units of resistance. So this is a trans resistance amplifier, right? We have an input current, we get an output voltage. So now we're working with a trans resistance amplifier, so this has units of resistance. Okay? All right. All right. So now, how do we do feedback for this circuit? Can we do series feedback? Here's the, look at this now. Let's start off with, okay, can we put something in series here? Not really, right? I mean, the current source, you can't put something in series with. The current source sets, if I have a current source and I put a feedback in series with it, you know, this is I in, this is I feedback, this doesn't work, right? There's no differencing. So I got a difference. So how do I difference when I do currents? Well, I do it like this. So here's I feedback, here's high in, and so at this point here, I air is equal to I in minus I feedback, right? See that? Notice this is in parallel. So this current feedback is now in shunt, okay? So we call this shunt feedback, okay? How am I going to sense the output voltage? I want to sense it in parallel, just like I did before. So I take this down. I take this down. So this is V in of the feedback network. And notice it's in parallel with the output, so I'm sensing the output in shunt. So this is shunt feedback. Current in, voltage out. Okay? Now, let's go do all the little calculations I did last time for this case. So here's a cleaned up drawing of it. IN, here's the feedback, here's RN, here's R out, here's this trans resistance thing, here's the sensing circuit. I go through and write my little formulas. You know, I feedback equals FG. Oh, now, here's something else to notice. What's F? F is the feedback factor. Okay, always the feedback factor. Here's the feedback circuit down the bottom down here, going in this direction. It's sensing the output voltage, and it's creating a current. So F sub G is equal to I feedback over V in feedback, but V in feedback equals V out. So this is the same as I feedback over V out of the closed loop circuit. So what is this? This is a conductance. So F sub G has units of conductance. So the loop gain, T, is A sub R times F sub G, right? Units of resistance times units of conductance. So T, again, is unitless. So always make sure that T ends up unitless. Right? So you have a transresistance amplifier and a transconductance amplifier. In the loop, if you go around the whole loop, then you end up with a unitless situation. Okay? So let's take this. We write our little formulas. You know, I feedback equals Fg times Vo. F is our feedback factor. Fg equals, you know, and so on. I error is equal to the difference of the two currents. You know, going on and on. V out equals this. And you end up with V out over I in equals this. 1 over Fg. Fg is the feedback, transconductance feedback factor times T over 1 plus T. So it's exactly the same as we had before. 1 over F times T over 1 plus T, except now this has units of conductance, and 1 over that is resistance, just like we have to have, because the units, the input is V out over I in, right? So we have to have units of resistance in the end. And it's 1 over that feedback factor that gives us those units. Okay? Yes?
But then it's not the R over the R again. So how do you make this accurate, just like last time?
Well, it is. No, it is accurate, actually. Yeah. I'll show you a circuit that does it in a second. Okay. Yeah, this actually will end up a function of resistances again. I'll show you a circuit in a second. Okay. Okay. Let's do the Rn calculation for this thing. I did it here in the notes. Rn is V air over Rn, so we calculate what this current is here. That's this current voltage divided by that current. And then you figure out, you know, substitute in for V air, and you get this, and calculate I air. And you end up with Rn is equal to this. Rn of the basic amplifier divided by 1 plus T. And what would you like to have? Think about it. Remember, we have In, and this is going into an amplifier. What would we ideally like to have that amplifier look like? We'd like to have it look like a short circuit, right? We'd like all the current to go into the amplifier, because if we have some source resistance, a perfect current amplifier has a short circuit on its input. So sure enough, this thing gives us a low valued input resistance divided by the loop gain. What's the output resistance? This is a voltage output. So we'd like to have that be a low valued output resistance. Can anybody take a guess at what the answer is going to be for R out? It's going to be R0 over 1 plus T. It's what the best thing could be, it could be, right? Negative feedback makes it always better, right? I did the calculation here, and there's the answer. You can go through this yourself, right? How do you do these? So this is a shunt network. Current in, voltage out. It gives smaller values of resistance on the input and output. Now, there's some so this is kind of the input. This is the sort of the output. You know, this is how the feedback senses. This is how the feedback is put back into the input. Notice when it says, here's a little mnemonic device for you. When it says shunt, it's smaller. Okay? So if you can figure out that it's shunt feedback, you know what the formulas are. It's going to be small, small. Rn divided by 1 plus T and R out divided by 1 plus T. So shunt is small, right?
Is that why they call it shunt?
No, shunt just means parallel. I think it's just an old way of saying parallel, right? What? Back in England, when they first discovered this, right? I don't know why. Take your history class. What do you go to history for, right? This is engineering. Go to history class for that stuff. Right? History of technology, right? That's what we need. Right? It's a pretty archaic word, I would agree. We could change it to parallel if you'd like, right? makes it. Look at this. This is really good. Oh, that's series shunt feedback. It really impresses your friends, right? Because series shunt. What's he talking about, right? So it's pretty classy that way. You got to have a few of those kind of things to make you feel good, right? So, okay. But that means you have to figure out what it means. Now, that's the challenge right now. So let's look at an example of series shunt feedback, and I'll give it one to you. Let's drop all the way down to a transistor. Okay. So good old. A basic amplifier can simply be a single transistor. Okay. So let's use this as my basic amplifier. Good old common source with a current source load. Okay. Let's put some feedback in this circuit. Let's take the output, which is V out, and let's feed it back into the input. And let's now have an input as a current. IN. Okay? So this, I claim, is shunt feedback. Now, how do I get that? So this is the feedback network right here. That's the feedback network. So let's redraw the feedback network like we did before. So here is a V out, okay, on this end of the feedback network, okay. Let's call this RF. RF. Right. And if I want to figure out how much feedback current I have, how do I figure that out? Here's what really gets confusing about this feedback stuff, okay? Clearly, let's look at this case right here. How would I figure out how much current I have coming out of this feedback network here on the bottom? What would I do on this side? Let's treat the feedback network by itself. What would I do on this side in order to figure out how much current is coming out of the feedback network? Would I put an open circuit there, or would I put a short circuit there? A short circuit. Exactly right. We've got to short this in order to see how much current is coming out of this thing for the feedback current. It's got to be short. We can take the feedback network and short it. If we look back at our previous case, let me jump back a second. We implicitly, though I didn't say it, when I calculated this feedback factor, what did I put at the output here? An open circuit. I didn't short this output of this feedback network. I put an open circuit there because it's a voltage output network. So a voltage output network, to find the value of it, what you need to do of a two-port, you need to open circuit it. For a current output of a network, you need to short circuit it. So in other words, for me to figure out what the feedback factor of this circuit is, I will short this. Right? So here's I air is going in like this. This is I feedback in this direction. So I need to calculate I feedback is in this direction. So I feedback is going to be equal to what? Minus V out over RF. So F is equal to V out over I feedback. Oh, whoops. I feedback over V out. Remember, this V out is equal to V in of the feedback network. All right? Watch these V outs and so on. So I feedback over V out, which is V out of the closed loop circuit, which is the V in of the feedback network. This is equal to minus 1 over RF. I've left out this resistor right here for right now, and I'll care about this a little bit later. In fact, this could be infinity right now, so as far as we're concerned, don't worry about that one. Okay. Now, um, what's V out over I in? So I give you this circuit, V out over I in, and let's say this has a lot of gain. What is V out over I in equal to? You tell me? Let's say this is transistor GM, output resistance R0. Say this has our output resistance R0 current source. What is V out over I in? It's 1 over F times T over 1 plus T. So let me say T is much, much greater than 1. T is much, much greater than 1. This goes away. So this answer comes out to be simply equal to minus 1 over RF. So it's coming out to be minus RF. So the ratio of output resistance to input resistance of this circuit is simply 1 over RF, or RF, that resistance right there. Question? Go ahead. How I got this? This right here? Where did this came from? So let me redraw this again. So let me draw it in this form. Look closer to this for a second. Okay, let me try that. So here is our current source. Here's our input. So it's in shunt, right? So we take our output here, and then we take our, so here's V out, here's V in feedback, and this is a ground, and then this goes through a resistance, RF. This RF is connected up into here, and this, here's our I in, which goes to ground, and okay. So this, I claim, is the same as this. I didn't put this resistor in here, right? We can include that resistor. This resistor is going to give you a lot of pain, so let me just, I'll worry about it a little bit later, okay, right? So, okay, so you see that? So now we need to calculate what this feedback factor is. How do we do it? We take this output and short it. And we figure out, we apply a voltage here, and we see how much current goes into this feedback network. Okay, and feedback factors like this, so we got to figure out how much comes out of this feedback network. So we short it. And I could short it up here if you want to look at it that way and calculate what this short this point and see what that feedback current is. Okay. Shunt. Okay, here's another way to look at this thing. To figure out the feedback factor when it's shunt feedback, in other words, I'm feeding back a current into the input, it's short. It's just shorted, right? So shunt equals short, right? Shunt equals small and shunt equals short. So when it's a shunt type feedback, you short the output to be able to see what the resistance value is. If it's series feedback, you open circuit it. So series open, shunt short. Okay? IN minus IE, right? Here? This is I feedback. This one here. So what's the current here? Yeah. Okay, here's I error. That's why I said this resistor. That's why I put that resistor there. All right. This bothers you right now, right? Because you see this goes into an infinite open circuit. So I'll put a resistor there for you for a second, Rn. In actual fact, it won't matter whether I have that resistor there or not. Okay, so just wait a bit, okay, and I'll show you that. But so if this makes it look a little better for you now, right? Right? There's a place for that current to go. Otherwise, the current has to be 0, right? But it turns out you don't have to have this resistor here, so everything falls out. Let Rn go to infinity, and we got the normal case we talked about. But I'll come back to that. What am I not including right now? What I'm not including, which I'm going to include, and it'll take care of this kind of thing. Notice I have an ideal feedback network. It's open. This is open circuit voltage, and for this voltage one, I had a perfect voltage output. I have no R in of the feedback network, and I have no R out of the feedback network. I'm ignoring the resistances associated with the feedback network, and clearly they're there, right? Because here's R2 and R1. So what I'm doing right now is I'm not. So here's the way we're going to do these problems. I'm including the basic amplifier with its non-idealities: finite input resistance, finite output resistance. I'm right now not including the non-idealities, the finite input resistance and finite output resistance of the feedback network. What we will do, after I go through all 4 cases, I will then put in the R in and R out of the feedback network and get a new set of equations. And that's when we'll take care of the stuff that you're worried about. That may not be obvious, but there's always a resistance there because it's coming from this feedback network, right? So that's how it shows up. Okay, I'll give a couple minute break. All right. Soon, yeah. I'll hopefully by tomorrow. Yeah. Okay. So Rob's job.
You had a plus here and then you crossed out for a check. I made it really short, and I thought I made it pretty concise. I just want to know how.
I figured out it was you, and I thought, and then I thought, I can't give him a plus.
Which one am I?
Tamir Bashik, it's clear. And yeah. Oh, so it was close.
Yeah, I know, but you crossed out. I just want to know why. I mean,
I don't remember. It's all relative, right? So I just kind of had
it
a.
doesn't matter. You probably only give it a 95 anyway.
That's exactly right. That's the only difference with that.
So that's not really much.
Yes.
Our question is that I don't really understand this. Not this one. The shunt. Right. I don't see how that relates to this. I really don't see that.
Here's the basic amplifier. Here's an input. Here's the output. Right?
Right. Well, input's supposed to be infinity anyway for the.
Okay, so like I said, it could be that be infinity.
Well, I mean, just get rid of that.
Okay, get rid of that. Okay, and then get rid of that. So then, and this is GMR out. This is R out.
Uh-huh.
Here's the 2 outputs coming down. 2 outputs coming down.
Okay.
Feeds into RF. Here's RF.
But there is no RF.
As I said, I'm not including.
Maybe that's why I can't see it.
It's like a 2-port, right? It's a 2-port, and I'm not including the input resistance and output resistance of this.
Okay.
This is a V out over RF, right?
Okay.
This current here, right? So that's just what a resistor is, right? It's a function. The current here is going to be V out over RF. So I'm making this equivalent to this without including the input resistance and finite output resistance.
Okay. Well, also, you said, your A is now your closed loop gain. No, that's the closed loop. Your open loop gain. Your gain. Your A is now a function of 1 over RF, right? It's 1 or just RF.
1 over F.
Just over F. 1 over F, and F is just like.
And F is 1 over RF.
1 over RF, right? So just RF, right? But I thought it's not accurate to make a resistor its exact resistance because they have a big error percentage. But then ratioing 2 resistors is easy.
Yeah.
It's inaccurate, but this is not really accurate. So that's.
After break, I'll show you that. I'll show it to you.
Show me how this will be accurate.
Yeah, well, I'll show you. It's a ratio because we don't usually come in with the currents either, right?
Current source.
So we usually come in with, so we usually have a voltage source input, right? So the voltage in, this is our source. Voltage in will be equal to I in times our source.
Okay.
So it'll be the ratio of the source resistance to RF.
So last 3 points out of 5 percent or not.
What?
I don't understand.
What?
3 points.
We're hearing you complain about the 3 points, I guess.
Right.
Yes, 3 points?
Not.
Not that important.
No.
Being taped, right? So, right.
I have even so that we can divide it into 3 parts, the gain of 1000. Then we have different value for GM for each part.
This is very much approximation.
I mean that this GM, when you give the most current to the one stage, you have a big value for GM. But when you have 3 parts,
It's it'll be just sort of approximate value, right? So just approximate.
oh,
Okay. Oh, he's so icy. Keep scanning around. Having some fun back there, right?
Like for this feedback, but like usually like inside this circuit we have a like let's say differential payout wave, then the input resistance will usually be infinity, right? But then how this like shunt will help us because it seems like even though we divide it by one plus t, it's still infinity.
You have to, the problem is, what will happen, I include the finite output resistance of these things here. It'll be, say, wait until I include the finite input and output resistance of this thing here, and then it will be that resistance divided by 1 plus t.
Oh, okay.
Okay. Okay. Got a nice break. Let's do 2 more. Okay, roll 'em. We're going. We did series, shunt. So here's shunt series. Shunt series is going to be current in, current feedback with current sensing. So this is the first time we've done sensing now. Now notice how the sensing is being done. The output current, so here's our output of our circuit. Here's an output current, okay? And notice it's in series here. Here's goes in and we're sensing that output current, all comes together and goes into our feedback network. So we're sensing the output current in series with the output of the amplifier. Okay? So this is very different from when you generally think about op amps. You can't really do series sensing. You only get a voltage out of a typical op amp. So when we do series sensing, we're actually having to work with our transistors. Okay, and I'll show you how to do that, okay, in a second. But basically, it's the sensing's in series. Now we're feeding back in shunt, so we can see that just like before. So it's in parallel with the input. So I air is equal to I feedback minus I in. So here's a shunt series. And so what are the answers? Okay, so I out over I in, so this is a current amplifier, is going to be equal to 1 over F, the feedback factor here, times T over 1 plus T. And this is a current ratio. The feedback is a current ratio as well, I out to I feedback, right? What is Rn of this circuit? Looking into here, Rn, what is that going to be? Little Rn times or divided by 1 plus T? Divide? Why divided? Shunt small, right, exactly, right. Or another way to think about it, it's a current input, right? What'd you ideally like to have? You'd like to have it small, right? Okay, so Rn divided by 1 plus T. R out. We have a current output now. What's an ideal current output? What's an ideal current source? High resistance, low resistance? Right? R out times 1 plus T. It's not shunt, right? Series is high, right? So it works. So I did the calculations here. You can do those, but This is the answer for shunt series. What's an example circuit of that? Let me think. Let's think of an example circuit of shunt series. I can't think of one. I'll come up with one in a minute. Right. Let's do the last one, and then we'll have some more. Right. Series. Okay, this is voltage in, current out, and series means it's going to be multiplied by 1 plus T for the input and output resistance, and the gain is just like before. It's going to be this is a transconductance amplifier, right? Because it's an output current with a voltage input. Okay. So there you go. So that's so there's all four cases. Series, shunt series, all four of them. Okay, so now let's start doing some examples. Okay. This one we've sort of done already. Series shunt I like. That's an easy one, right? So, but let's just put the numbers in. That's kind of why I wanted to do this. Excuse me. So let's say open loop voltage gain of this basic amplifier is 10 to the 5th. Let's let R1 be 1 k ohm. Let's let R2 be 9 k ohms. Let R0, the output resistance of this, be 10 k ohms. Okay? The feedback factor of this thing, we just calculated that before, it's going to be, if R1 is 1 k and this is 9 k, the feedback factor is 0.1. You know, it's 1 k over 9 plus 1 k, so it's 0.1. The gain of this is going to be what? What's V out over V in going to be? If F is 0.1, what's the gain? 1 over F, approximately, equal to 10, right? What's T? T is equal to F times AV. F is 0.1. AV here, the voltage gain of this amplifier is 10 to the 5th times 10 to the 5th. So that means T is equal to 10 to the 4th, or 10,000. So T is clearly much bigger than 1. So this thing's going to be very precisely a value of 10 if these ratioed resistors are 10. Okay? What is the input resistance going to be? Input resistance, we said, was infinite. Well, infinite times 10 to the 4th is still infinite. So it's really good input resistance, as most of our circuits really are usually pretty good. What about the output resistance? R out is 10 to the 4th ohms. We said 10 k ohms, divided by 1 plus T, which is 1 plus 10 to the 4th. So our output resistance thing is 1 ohm. So think about that. 1 ohm, you can drive, like you've been trying to drive these 1 k ohm resistors and how tough that was, or drive that, remember? With this feedback, you'll have a 1 ohm output resistance. You could drive 10 k ohms or 1 k ohms with no problem at all. You could drive 50 ohms with no problem at all. So this feedback, in some sense, takes care of one of the big giant limitations we had, right, in trying to make good amplifiers and stuff. Before we can take the gain and turn it into really low output resistance so we can really drive something. So that's pretty neat, right? So feedback really is a very useful thing. Okay. Yep.
I can't see how. Can you just show why the low output make you able to drive it easier?
Because, like this. Let's take the 2-port now of our base. So I have this circuit right here, but let me just do a 2-port now around this whole thing. Okay? My 2-port around the whole thing looks like this. It has an infinite input resistance like I did before, but now it has an output resistance of 1 ohm and a gain of 10, right? Times V in, right? So I can drive 50 ohms here, and what gain am I going to get here? It's going to be a voltage divider between my 1 ohm and 50 ohms, right? So this looks like a, 1 ohm. There'll be no voltage division at all. So this will be exactly 10 times V in here, right? So this 50 ohms is very large resistance compared to the output resistance of this circuit. Okay? If I had 50 ohms here for an output resistance, I'd lose a factor of 2 there, like that. And I become pretty much independent. It's really set by that ratio of resistors. Okay? Okay, so here's, so let's go back and do the series shunt case, and then we'll, the shunt case rather. This I claim is shunt. So let me go back, let me do this one for you. Okay, so here we go. So here's our basic amplifier. Here's V out. You know, this has a this minus input. This is now. You look at this, and I claim this is shunt feedback. That means current feedback with current sensing. Now you look at this amplifier. Does that look like current feedback? So this is what's really hard about this feedback stuff, okay? You can't just look at voltage in and voltage out to sort of give you a clue as to what's going on, because the feedback is more a fundamental property of the circuit. What we choose for V in and V out is kind of up to us, because I can do a trivial modification of this circuit. All I have to do is this. Take this and do the Norton equivalent of this input. Right? I can turn this into V in over R1, make this R1, then go into my basic amplifier here, right? Here's V out. And then there's, of course, there's a ground here. Right? I guess this is right. So now you can see this, here's my feedback network. This is R2, okay? And you can see that, and so here's the current, I feedback, and here's the current going to here, I air, right? And this R1 we've got to take care of, okay? And I'll do that in a second, okay? V in over R1. So you can sort of see, so you can see that the current being fed, this is being fed back in shunt with the input. Even though it looks like I have a voltage here, it's really a parallel combination. See, it's in parallel here, as opposed to this case here. So notice here I difference the, here's the input in series, here's the output in series. But here the input and the feedback are in sort of parallel with each other, and I have to turn into this current to really show the parallel combination of those two. So I'll agree. This is not easy to see, but it's, you're going to have to see it, right? I mean, this feedback's in parallel with this input. It's not in series in any way. I mean, here's the input to ground. The trick is find out where the differencing is going on. Find out where the node that there's a difference. Identify the error. See, there's no error voltage being developed here anywhere here, right? I mean, here I had an error voltage being developed by this minus this. But here there's no error voltage being developed. It's something's happening on this node here. It's a difference occurrence. Here's I feedback, and here's I air coming in there. So it's a feedback current. Okay, see that? Now, what about this R1? I kind of let it flop around. There's two places I could include it. I could include it as part of the feedback network, or I could include it as part of the basic amplifier. Your choice. The answers will come out the same. I'll give you problems. You say, geez, where should this go? What's the feedback network? What's the basic amplifier? It won't matter when we finally finish up and include the non-ideal effects of the feedback network. So take my word for it. You know, don't get bothered by this because it's going to bother you. I'll tell you, it bothered me, right? So, so here, so let me redraw this again. Let me include. So let me this time include the R1 as part of the feedback network this time. Okay. And oops, no, I'm sorry. So this is Vn over Rs, right? And it's a current. And here is I feedback, and here is I error. Okay? And don't worry about the fact this goes into infinite impedance here. It's not going to be a problem either in the end. Okay. It's just a little bit of problem now as we're going through this. Okay. So now it's really clear, right? This is a difference. It's the feedback currents in shunt with the input, and all this is the feedback network. What is the feedback factor? This is V out. How do we figure it out? We short the output, right, and drive the input. So if I short this output right here, I feedback is going to be equal to what? Minus 1 over R2, right? The feedback network is unaffected. The feedback factor is unaffected by where this R1 being down here. Excuse me. How's that? Let me just die here first. Okay. So notice it didn't matter. I brought this resistor down to the feedback network, but it didn't matter. Okay, so that seems good, right? If it made a difference on the feedback factor, if I included it or not included, we'd kind of worry, right? Because this is such an important factor. Okay, now remember, let's say the loop gain of this is high. So V out over I in, right? This is equal to I in, is equal to 1 over F, right? Which is equal to 1 over minus 1 over R2, which is equal to minus R2, right? Here's the problem you had, this absolute value of resistance here. But now let's take I in and replace, let's say what I really want to do is look at V out over V in, because that's kind of the problem I initially asked for here, V out over V in. So I let this equal to V out over I in equals V in over RS. Right? So you can see that if I multiply both, take RS, I can bring that up into the numerator here. From there I can bring it over here. So V out over Vn equals minus R2 over RS, or R1, I guess, right? I'm sorry. This was my RS, so this is R1. So V out over Vn equals minus R2 over R1. It gets back to this problem here. So here's the procedure. You got to go in there by looking at the circuit, figure out the topology, figure out what kind of feedback it is, convert the input to be consistent with the type of feedback. Okay? Then go through and start doing our little calculations. Figure out what the feedback factor is, figure out what the input resistance of the amplifier is, figure out what the output resistance of the amplifier is. Because I could have done this a different way. So let me do a second way I could have done this problem. Instead of including the output resistance down here, or this R1 down here, I could have done this. Here's that IN. I could have put that input resistance, R1, across the amplifier. R1, R2, and here's V out. All right. Okay, so here's the feedback now. It's R2, and F is still going to be the same as before, minus 1 over R2, just like before. Okay. Now our basic amplifier, instead of an input resistance of infinity, is going to have input resistance of R1. Now you say, look, that's changed the problem. Because before I had, Rn was equal to Rn divided by 1 plus t. We know that. So in first case, Rn was equal to infinity, so it was infinity divided by 1 plus t. Now this case here, it's going to be R1 divided by 1 plus t. You say, well, those are not exactly the same. It's only true right now because I'm not including the finite output resistance and input resistance of this feedback network. We're going to include that pretty soon. When we include that, these answers won't be different. We won't see these two different cases. So it's only showing up now because we're not doing the whole problem at once. And I'll do that next lecture. And then you'll be satisfied.
One example. I want to use feedback. Maybe feedback.
It'll stability stuff.
Oh, so it'll also. You can't put feedback in there. You say you can drive a big or a small load.
Yeah, but you got to deal with stability.
I don't really see how to make this more original now because now everyone knows how to do the thing in a couple game stages. So we're left with the same problem as we're gonna have the same design as everyone else and just gonna get the check mark.
The check mark was for the.
No, I also got a check mark for the design.
Oh, design.
Why won't feedback work?
Because of the stability.
Even if it's negative feedback?
No, that's because of the frequency response. So,
Vậy chừng nào chị mới làm cái
well,
ấy vậy?
don't worry too much about that. I will count that even less. Okay.
What?
Most people get all the same. I won't.
That's the problem when everyone gets the same thing.
Or do you know our names enough that you can recognize them on the project?
Joshua?
Yeah.
I keep telling you so you recognize it.
Keep going. Keep telling me. That'll help.
Professor, here is an infinite resistance. So how comes I error is going in this? Actually, I error here is 0, right?
That's what I was saying. Right now, don't worry about that. Okay?
Okay.
I'll take care of that later on. Right? You can think of this being a resistance here, and right now it happens to go to infinity, but next lecture, it'll all be taken care of. Okay?
Quick question. When we are looking at the